business and you want to be able to deliver things in under 1 hour, you can hire a steward for doing that. And among other things, the main let's say project we have worked on has been Okay, yeah. So I have been doing a simulator for this kind of thing for them. All right, and that's the thing that I am going to present in this meeting. All right. First of all, I would like to introduce some vocabulary in order to to communicate better, and we have all the same jargon in mind. All right. So these are like keywords in this sector, right? Job is the models the idea, of having a package to deliver to someone, and you have an origin to pick the package, and then you have to deliver the package in a destination, or maybe there's also possible to have more than one destination, right? One origin and let's say one destination, could be more than. That's the idea. Job, origin, destination, right? Then we have drivers. Drivers are the people in this map. So these colored dots symbolize drivers, right? These are people working in Paris at some time. Then drivers can be in a number of status. They have like a steam machine, and the main ones are being on duty, which means that the person that is doing the job is active, is working, let's say. Off duty is the negation of that, is just at home, whatever, is not working, off duty. And then being busy means doing a delivery. All right. Those are the main driver statuses. Dispatch is jargon for the selection of a driver for a particular job. So you get a job, please deliver this thing from this, you have to pick at this point and then deliver at this point, and you have a number of drivers right here. So dispatching means selecting the best fit for that particular job, right? Depending on some heuristics, right? That's dispatching. And the dispatch algorithm is the algorithm that does this. Pickup means picking the route that you have to deliver, and drop off means leaving the thing at its destination. Okay, so we have now some jargon to be able to communicate better. Right. First thing first, which is the motivation of this simulation? Doing this thing technically is super interesting, but what's the goal, the end goal of this? The end goal is to be able to test new business rules, all right? So the same thing that we say, to understand the performance of something, let's benchmark, okay? Instead of figuring out from intuition, whatever, benchmark. This is the same thing applied to business. So instead of wishful thinking about which business rules could the business change in order to perform better, the idea of the simulation is to be able to put those things in place and see how they perform business, right? So for instance, one use case. Evaluate this possible tweak in the dispatch algorithm by simulating what happened yesterday and compare KPIs. That would be like a use case. So the dispatch algorithm is not trivial, all right? So maybe you have an idea, okay, maybe this improves the dispatch algorithm. So instead of just doing that, the simulation gives you a way to actually measure which is the impact on existing data, all right? So we can simulate what happened yesterday with the new code and see how it performs. And you are going to be able to perform more informed decisions this way. That's the whole point of doing this project. So this yields a key, I would say a key design driver in this project, which is that the simulator should optimize for a faithful replay. because if the word simulation for many people is going to mean different things, many different things. It's going to resonate, and maybe some people really think on visualization, other people, I don't know. You know, it can mean many things to simulate something. So this is key. So we want to optimize for faithful replay. In particular, not for speed. Not for speed means speed is good, but faithful is first. We're not going to sacrifice speed by not reflecting what happens in reality up to some point. We're going to see that you cannot duplicate everything, but this is important, not for speed, not for performance benchmarking. Okay, so the goal of this project is not to change code and see if this runs faster. That's not the point. Okay, if you improve the code base, then as a byproduct, the simulation is going to run faster normally, right? But that's the other way around. Okay. And as a consequence of this key design thing, we are going to treat the application as much as a black box as possible. As much as a black box as possible. Okay? So, think integration tests. We are going to try to execute, to exercise the entire system as much as possible. Okay? We start with a database dump taken at some point, and we have a time window to simulate in the past. So the database dump has that time window included, and then we have a replay date for replaying the things that happened at that time window. Okay, this is the input data. This is all we have. From this data, we are going to recreate the things that we can the most minimum things for simulating what happened in that time window, which is job creation, which jobs did we have yesterday. Let's think yesterday as a simple use case. When drivers started working, when drivers stopped working, so which people does the system have available at some point in time, and finally coordinates for all these things. So a job is created for which origin, at which point, which destination, drivers start working, where are they situated, so you can put them on a map or whatever. You have to know the location of everything because the location of these pieces is instrument, okay, so for the logic of the entire system. Okay. All right, and then there's external behavior that you have to emulate somehow, and we have here to simplify some things because something like a steward has like the internal let's say the internal logic, what everything that is happening internally in the servers, let's say, but then there's an important external part of the system, which are the people that are using mobile phones, and if you are going to simulate this thing, you do not have these people. Okay, so for instance, when the dispatch algorithm selects someone, it sends a job invitation, and that someone can accept or decline. All right. Well, there's no one here to accept or decline, so we have to do something about this. And what we do at this point is just accept everything. It's like a simplification that makes sense. All right, and it's known. So there's no business rule that you can compare here that depends on business. On job invitation acceptance at this point. Okay, maybe this can change in the future, but then driver free riding, for instance. If you start working with a bike, normally you are not on the spot. You take the bike, you say, I am ready, but then you go and ride, randomly, let's say, okay? We cannot do this. We could, and maybe in the future we do, simulate some random walk, but this is something external to the system. Waiting times means that when you go to pick a package, that's not instantaneous. Maybe you go, there's a person that is attending someone else, and you need to wait 10 minutes to get the package, all right? That's something external as well. Traffic and other variables, all right? That just, they do not happen inside the servers. Okay, we have the input and we have these remarks, and finally what we have to produce is an activity log at this point, some stats and some KPIs. KPIs in the end is the most important metric, right? Okay, so we are going to see the design of this thing. These are the main design from an object-oriented way, if you want, right? We have something that loads events from the database, those first events that I mentioned, job creation, when drivers go on duty, that kind of thing. And there's an initialization of the database, and the second one, the initialization of the database, is a very tricky part. So it's the most tricky and most time-consuming part of this project, surely, but it's the less interesting one from a technical point of view, so we are not going to see it. The problem here is that you get a dump of the database and you have to simulate a certain time window. Okay, but the state of the wall, when you get the dump, the state of the wall is the state of the frontier of this dump. So if you have an API for checking the current status of some driver, the current status of some driver is going to be the current status, the last one. Okay? But in general, you want to start the simulation with the state of the wall as it was at the beginning of the time window. Okay, that's for the entire database. So this is something tricky and time-consuming, but we are not going to see it because it's just SQL and and knowing the application in the end. The runner is the component of the system that actually runs the simulation and has the main loop. The time wrapper I'm going to explain, and the active job adapter is in a custom adapter that we have written for this project that I am going also to cover later. Okay, you can imagine that this is the main loop, and this is one of the first things that I wrote, because when I design something, I always think first about the interface. Okay, if we're talking about a website, for instance, what I want to see first is the interface. Because the interface, if you have the interface, the rest mostly follows. Which is the models, which are, I don't know. If you can see which is the interface of something, the rest follows. And the same thing for libraries. Okay, the first thing that I think is how third-party code going to use this thing. And if you get that API right, then the implementation follows. All right. So this is like the goal. I want the main loop to be this simple. All right. An event is something very simple. It just has an interface, fire that does whatever it has to do, and we are going to subclass this thing. And then it has an epoch. I like epochs. So epoch is the time at which the event has to fire. All right. So the time that job that you are simulating was created, let's say. All right. I like epochs because they are very simple. They are integers. They are monotonic. There's no time zone or anything going on. Well, there's UTC, but there's no conflicting time zone going on or anything. Very simple. You can compare them trivially. I love them. So in order to represent time in this project, I am using epochs everywhere. So an event is something as simple as this. And this is an example. For instance, this event simulates when the driver picks the package. Okay? Right. So, as I said, we are going to use the application as much as a black box as possible. that is not going so far as doing HTTP calls, not so far, but you could say that each one of the fire method of each one of these events has what it has to do is encapsulated in some very high level method call. So that's the level of high level that we are working with. All right. The scheduler. You're going to see that the things are in general very simple, and that's also something that I have tried to keep constant, like simplicity of everything. Like a scheduler can be something very sophisticated if you want. No need, man. Just take a sorted set. So the scheduler has to know in which events there are in the system, in which order they have to run, and you have to be able to say which is the next event, or pick which is going to be the next event, shift that next event from the queue. All right. This is a very simple trick, which is to use a sorted set. This comes from the standard library. If you require set, you get set, and also a sorted set. A sorted set is a set that has an order. Okay, so a regular set doesn't have an order, but a sorted set is a set that has an order. The order in Ruby comes from this thing, all right? And if you throw an element to this collection that implements that, is going to be sorted for you. So a scheduling trigger, just a line of code, right? And this is also used typically in Redis that has sorted sets. Sorting things that have a timestamp associated this way is, I have found a number of use cases where this is very powerful because it's super trivial and it solves a problem that otherwise would be more tricky. So nothing fancy, just a sorted set. So we have here our main loop that is asking the scheduler for the next event, done. Okay? This is an external iterator instead of doing what is more common in Ruby, like doing each event or an internal iterator like that. Why? Because events, and we are going to see it now, can generate other events when they fire. Okay? So it's not like we have a fixed collection and we are doing that. So when you fire this thing, maybe this event is scheduling more events. So I believe an external iterator communicates that better to the reader of the code than an internal iterator. But we have some time constraints for these events. The events have a timestamp. They are replayed at a different date that belongs to the input data. But this is very important. They have to be fired at the same time of the day that the original action. Okay. So if the job was created at 2 p.m., we need to create that job at 2 p.m. This is important because maybe some business rules depend on this. We have that time constraint. So one way of doing this is running at 1x. So if you have to reply a time window from 11 to 11, so everything happening at the time that it took. And that's it. It's going to take 12 hours. We would like to be able to run this faster than real time because time window can take a few hours, right? So how to do this? So with the time machine. The time machine is this thing. Basically, the idea is that it is not uncommon that from some event to the next event there's a time gap, maybe 5 seconds, something like that. So can we save those 5 seconds where nothing is going to happen? Yes, we can. We change the system time. All right. So this is the same main loop we had before. With this little trick, we're going to set the system time to the event epoch, and then before we fire the event. So as far as the system is concerned, is the time of the event, and we have saved 5 seconds. A reminder, we have two clocks in a computer, all right? We have a hardware clock, also known as a real-time clock, which is a physical clock that, that has an independent power. So if you take the power off of the computer, the clock runs. And it can be managed with this utility in Unix. Then we have the system clock, which is the one that we normally interact with. The system clock is when you ask for the time of the system, you get this one, okay? The system clock is interesting because it is not a clock. The system clock, when the system boots, starts, so the CPU is sending like ticks, okay, to the system, and the system counts these ticks. So the system basically, when boots, checks the hardware clock and says, okay, now is this time. And from that point on, it has an integer with a counter of ticks. Okay, so the system clock, then when you ask for time now, for instance, it has to take this integer and do math and then show you the time. But behind the scenes, it's just a counter of ticks. Interesting, right? There are some daemons that reset this thing, and Linux has a mode called 11-minute mode, where every 11 minutes the hardware clock is reset with the system clock, and that's what you have running with NTPD. NTPD checks the system, checks the time at somewhere, and then sets the system time, and then system time is in the end going to be reflected in the hardware clock. Okay, so we have a way to change the system time, which is just calling date. Also super simple, all right? Super simple. And a note here also. I'm shelling out here, all right? Just shelling out. And I know some people are afraid of shelling out, like this is dirty. I don't think so. Ruby, Perl, Python, they are all scripting languages. And scripting languages are glue languages. So if shelling out solves this tricky problem with one line, there we go. Shell out, no problem, all right? Wrap time, in the end, since we are touching the system time, in the end, wrap time that wraps the entire simulation resets the system clock with the hardware clock. So when you finish a simulation, we have moved a lot the system time, but in the end we reset it. So when you get the shell back, it's the correct time, right? Okay, so there are a few things being solved, but as simple as possible all the time. And this is to wrap up the simulation of a delivery, okay? So we have all the pieces, or most of them. When a job is created, the dispatch selects a driver. Then the job invitation for that job is going to be accepted for that virtual driver, because there's no actual driver going on. And then this generates events. So the actual delivery is performed through events. The driver is at some point, it has to go to pick up. Okay, so we move the driver, we compute flying distance, and we move the driver in a straight line, which is different from real life. In real life, they follow streets, but this is one trade-off for the simulation that is considered to be secondary for the purposes of the KPIs that are important to the business. Okay, so a straight line is enough. Okay, and we do not need to contact Google or anything. Everything is computed on the fly. So it picks the package, goes to the destination, performs drop-offs, and there's a regular location update. So the system needs to know where are all the drivers all the time. Okay, so with certain periodicity, we inform of the location of the driver while it is delivering. Okay, and this is computed depending on the transport type of the driver, which could be a bike or could be a number of things, and they have like a typical speed. We take that and we do some math, and you simulate these scheduling events. So every location updates, it's an event for updating the location. Drop-off is an event that does the drop-off, right? Let's go with active job. In the real application, there are many things that are going to be run as background jobs. Okay, so to remove as much as many things as possible from the critical path of one request, you move things to be run async. That's for performance, but in the simulation you do not need that you don't have that problem of like latency or whatever. Okay, so active job comes with an inline queue. The inline queue just does not schedule anything in any queue manager. You know, the inline queue executes jobs right away, but it is not able to enqueue jobs at a later time because there's no support. Okay, this comes with rails. Okay, but this is not good for us because there are a number of things that are scheduled to be run 5 minutes later or whatever. So we have a custom adapter for active job. Okay, the interface for active job is simple, and so we are. This one is in line, is the same one. Okay, so if you schedule something normally, it's going to be run in place. But if you schedule something in the future, then we have a custom event. So we have a scheduler, we have events, done. Okay, we have an event that means run this thing later. The scheduler is going to fire this thing, and this event is going to, so firing this event means running this one. So solved, no need to, everything remains within the simulation. Okay, there are a number of things that we do not need in the simulation, like external services, Google API, payment gateways. You have to put all these things, okay, because you are simulating, you have no business calling a payment API, you know. Push notifications to mobiles, there's no mobile, so no push notifications should happen. And then there are stuff external to the system. Does the client have funds, for instance, to be able to pay this thing? Job edition acceptance, we talked about this already. Is the driver's device reachable? For instance, this is something that in practice it matters, because maybe someone is theoretically on duty, but for whatever reason, the device is not reachable. So you have to take that into account when you have to invite them or whatever, because if the device is not reachable, doesn't matter the status. What you want is to dispatch with the highest probability to get acceptance and and get the best match for the job. So these things we do not control in the simulation. And I'm going to have some words on price of studying and reopening classes and modules, because for some people reopening they do not see it as a good thing. Okay, and I am very carefully avoiding the word monkey patching up to this point. Okay, I had to mention the N word. Okay, monkey patching. Monkey patching as a word is fine, but sometimes there's a nuance of monkey patching, like something dirty, something that is not, theoretically, very clean, whatever. I don't know. I love being able to reopen classes in Ruby. I mean, it has a number of use cases that if you do not have this, well, you have to go to more complicated solutions to do whatever you want. Okay, I have found, so as anything, if you abuse reopening things, well, you can theoretically create a mess. But I've been doing Ruby for 12 years, and my experience is that this is amazing, man. This is super powerful, and you have to master it and to use it, when the time comes. So we are going to use class reopening for doing these things. And as a discipline, every every stop or every decoration of things is just under the same directory. So if someone comes later to maintain this project, you go to that directory and everything that is reopened is there. So it's easy, all right? And this is a trade-off. The trade-off is we know that we are decorating some APIs with stars. If this breaks, this is not something to complain about. You know that eventually this could break. Some change in the application could break these stars. But that's a trade-off. It's fine if it breaks eventually. It's fine. You fix it, push, done. All right? Because the alternative is much more expensive. The alternative is redesigning redesigning the core product of the company in order to be able to switch to the production code, which is the one that matters, and also to some weird artificial world that we are inventing. I don't like that idea. Okay, you could inject, you could extract API, whatever, to be able to do that in an object-oriented, clean way that you have to do if there's no other. But this thing allows us to have the simulators as an external entity, and you hook into the production system in a way that the production system is untouched. Okay? So it's a very pragmatic trade-off, I believe. For instance, the device is reachable. Well, here the device is going to be reachable as long as the driver is on duty or is busy, like is working. That's done. How to force this in the simulation? So very simple. And I like, since we have prepend in Ruby, I like doing this kind of things with prepend. So the original thing is untouched, and then you prepend something, and if you need to call, the original code, you have super. I like this way of decorating things. There's a caveat here, which is modifying the system change, the chain of modules. So if you have a class that includes a module, and that class has this ancestor chain, all right? Okay, if after this code you, for instance, add a method to the module M, it's going to work. The dispatch of methods is going to find it. But if you include or prevent, if you change the ancestor chain of that module, then the class C is not going to find those methods. It's not going to find this thing. Okay, this conceptually is like, I think it's not consistent in Ruby. Like everything conceptually should be dynamic, and if you add methods, works. But if you include modules, it would work if those modules were present when you originally included the module M. But if you include them later, then this ancestor chain is not going to be updated, and that's because MRI makes a linearization of this, caches that, and that's it. So the first time the ancestor chain is computed, it's frozen. There's no code, going back to the ancestor chains that included that module to rephrase that thing. So in that case, just module eval, and one comment here. Normally, I use module eval instead of doing reopening module with the module keyword or class with the class keyword. Why? Because I want to decorate something that already exists. And this idiom makes sure that M is loaded at this point. Okay? If you do module M, well, you have to be careful. If you do module, you have to be careful that the module is already in memory to be able to decorate it. Okay? If the order gets reversed, maybe your decoration gets lost because the module is later loaded. Alright? So, with this simple way of doing things, you make sure that M is loaded here, because otherwise this is going to break. Alright? Finally, this loop is very understandable and deterministic and very easy, to work with. But for instance, if you have an event that takes 1 second and the next event is just half a second later, well, then you got some concurrency that comes from the real world. In the real world, we have events that are concurrent, and well, if we do everything sequentially, we are not going to be able to reflect this concurrency. So, in the last phases of the project, I added some concurrency here to be able to deal better with this actual fact of the reality. And there's a solution based on concurrent Ruby that has a thread pool and this thing which is a flag. Doesn't matter. Well, the idea, I'm not going to explain this slide, but the idea is that you fire each event in a thread, and you have a thread pool. The thread pool is determined by the pool inactive record, because you have a limited number of connections, and that's your hard limit. All right. So you fire threads, you fire events in threads, and you cannot. If you do that, you cannot just happily change the system time, because then you have in parallel things going on, and if you change the system time, that's global. Okay, it could confuse. So we change the system time only if the pool is idle. So if there's nothing going on and we have a jump, we do it. Okay. Well, that's the idea. There are details, but I am not going to get into that. And then the demo now, but it's a pseudo demo. So running a simulation takes time, but I think the talk deserves that at least you see what's going on, with all these things that we have explained. So I have prepared something which is an actual log. I did some edits to be able to fit better in the screen. I have an actual log of an actual simulation, and I just wrote a 3-line script that dumps this log in the screen. Okay, and it accelerates so that we can see how it starts, and then we are going to reach the end very quickly, which could take hours if we were doing a real simulation. Okay. So that's the current output of the simulation. With this log, we could, for instance, visualize what is happening, because all the information is here: which jobs, which drivers, where, how are they moving. Everything is reflected here. So with this, you could build a visualization of the simulation that could run, by the way, at any speed, because it's all here. Okay. All right. Okay. So in the end, we have some KPIs and some stats to breakdowns of the events, how many events, how many took, and yeah, from this breakdown, sometimes we have seen that maybe there could be some performance work to perform in some of the code of the application. That gives some insight in how the simulation is working. Okay, so that's it. Thank you very much. Questions?
Were you able to measure how faithful the simulation was compared to real nights, and see what was the difference in the error in the simulation?
Say it again?
Were you able to measure the error of the simulation, like how many jobs failed in the simulation and how many failed in the real?
Okay, so the question was if we were able to measure, for instance, which jobs failed and which didn't fail in comparison with reality. Okay, so yes, let me run this again. One of the KPIs, this project is very young, by the way, so it has not been used yet a lot to test actual things. So we have just ended the development of this. All right, but one of the KPIs precisely is to know which jobs expired. Expired means that a client created the job, but we couldn't find a driver to do that job. Okay, and after some time, that expired. All right. So that's a metric of the simulation. And this particular one is a little bit it has a bias. It has a bias because at this point in the simulation, everyone, as long as it is working, everyone accepts invitation. So the best fit gets the job invitation. Okay, in real life, the best fit gets the invitation, but maybe declines. Okay, and there are other things that can happen. Okay, since in this point we accept everything, there are less expired jobs. All right. This is the first version of this thing. It could happen that this is the base work, and now you can build upon this base work. For instance, now you could introduce some heuristics. For instance, you run some data analytics on who declines, how often, whatever, and then you try to include those heuristics in the simulation. That could be like a version 2, where these things is not going to be real life. It's going to be statistically reflecting what happens more or less in real life, but maybe you have something like this. Nevertheless, let me say that if you want to compare a business rule that you have changed, the business rule has to be compared. So the KPI has to be compared with the KPI of the simulation with the original code, not with what happened in reality. Okay, because those are different playfields. You have to run the simulation with the code in master, let's say, and then you run the simulation with the code in your branch where you have that implemented. Those are the ones that you can compare because they use all the same thing. Okay. Yes?
Is it possible to zoom on some point at the time when things happen very fast and you want to have data visualization of what is happening in SG with maybe a tool like Quantum GIS?
Okay, the question was whether it could be possible to zoom into some particular spot in time and be able to inspect what's happening there, in slow motion or whatever, in a way that allows you to visualize in more detail what's happening. Yes, I think it could be possible because in the activity log you have verifying. There's a lot of traces. So this was very fast, but there's a bunch. So the activity log was an interesting thing also to. It was interesting to decide what to log, because if you log too much, then you slow down the thing. If you do not log a lot, or if you log much less, then maybe you are missing information. So that was something that it was refined with time. And the log currently has, I believe, all the information that you will need to do that, and no more information than that. So it could be possible, because then you take the log and you take an offline tool that you write or whatever. And since you have everything there, all the entities, all the timestamps, all the locations, you could build a visualization tool that goes as fast as possible, that you have a timeline, that you can slice, that you can run as slow as you want. So it should be possible. Yes?
In these simulations, did you use the actual system of Stuart as a black box, as you explained earlier, or were you already plugged in? Meaning, were you using its API for job creation, treatment settings, and I don't know, whatever? Or were you already plugged in the system and called the real class method of this system through your simulation?
Yes. So the question was if we are treating the black box as calling the application, like doing like HTTP request or whatever, like you are really outside of the system, or we are plugged in. And the answer is that we are plugged in. So there's a balance point here. Doing everything through HTTP could be like the stream of taking the system as a black box, but it would have some consequences, like it would be much slower, and you wouldn't be able to modify the system. We need to modify the system. We need to not send notifications to a Slack. We need to not contact the payment gateway. We do not need. We need to not charge anyone while the simulation is going on. Okay. so this is like a trade-off, and the trade-off from the black box point of view is, okay, we are going to plug into the system, so the simulation lives in the same tree, and the simulation has access to all these constants to be able to reopen classes and everything. But so one stream would be that. The other stream would be to be two coupled. The solution was, fortunately, Stuart in general has a good design, and things are well encapsulated. All right. So fortunately, there was like APIs at the level of running the event in one line of code. Okay. So from the point of view of the simulation, if you run one line of code with one method call that performs that where everything is encapsulated, well, that's quite a black box. Quite a black box. You know that you have to call that method, but everything is hidden from you from that point on. So that was the balance point that we found. Or yes.
So it means that you are able to modify the configuration of the black box, meaning you can tweak let's say the black box, rerun the simulator, and see the result, and see if the configuration will improve, let's say, the number of sign-up jobs or other KPIs.
Exactly that. Indeed, the way that I imagine that is that, in general, the tweaks that you're going to want to do to the system, in general, I believe they are not going to be trivial. It could be that you are just, I don't know, you have a multiplier for, I don't know, tweaking the pricing of the service. Okay, you could play with different pricing strategies, whatever, you know. Maybe there's a factor somewhere that you change that factor. That could be trivial. But if you change the dispatch algorithm, that is not trivial. If you change the price strategy as in a more complex way, that's not going to be trivial. So that's a hypothesis. We have yet to see. But I believe the natural way to do this thing is to have a branch for the changes that you want to change. So there's going to be a setup. So the DevOps people are working on this. So you should be able to say, run a simulation with this input data for this branch. Okay, so typical use case, run simulation with the master branch, run the simulation with this branch that has 2 weeks of work doing something. Okay, and then you can compare those things. I believe that's going to be the most common use case. More.
So you can throw in the cluster 1,000 or maybe more simulation and choose the best algorithm to fit depending on the time of the year.
Yeah. So the question was if we can throw the simulation in a cluster of machines and then compare the results. All right. So this particular version is designed to work on one machine. So we have this is one application of that rule that get it right first and then make it fast. Okay, so make it right first was the serial loop. For instance, we had the serial loop for a long time. It was enough. It was simple. It was right. Then when everything was good, then we introduced concurrency. And concurrency gives you space for some load. But if the density of the events increases in a very dramatic way, then maybe one machine is not enough. So I'm going for the cluster part of the question. Okay. Then in the pipeline, there's also services that are going to run in different machines. Okay, and the idea for being able to run that, so for running in a cluster, there's an intrinsic problem, which is that we are changing the system time. So you can change the system time in your machine, but that's local. Okay, so the next step is also 2-line of code server in Sinatra with Node or whatever. 2-line of code server running on in all machines of a cluster, and then you need a coordinator. With a coordinator that says, "Hey cluster, this is the system time." You broadcast that. All the servers reply. They change. They shell out, and then you fire an event. For instance, if the dispatch algorithm is some external thing that you communicate that is a service in the system, you need to do that. Okay, and yes, and then you run this, and you run option A, you run option B, and then you compare, and yeah, that's it. Instead of deploying this, in real life, and maybe losing money, or I don't know, Okay, maybe last one. Okay, thank you.
Hello. Salut tout le monde, moi c'est Victor, je suis de chez Paris et j'ai un très bon talk pour vous, mais il commence à se faire un petit peu tard. Donc ce que je vous propose, c'est qu'on le fasse le mois prochain et qu'on ouvre le buffet là maintenant tout de suite. Est-ce que ça vous va? Levez la main si ça vous va à peu près. Ok, c'est pas mal. Juste 2 mots, on recrute chez Drivey des juniors, des seniors, des full stack, des back-end, c'est cool, venez, on est bien. Et aussi, on organise le Paris.rb workshop la semaine prochaine avec Rodolphe qui est là-bas. On va écrire du Ruby, ça va être cool, alors venez aussi. Et puis venez le mois prochain pour mon talk. Voilà, bonne soirée tout le monde et bonne fête.
Juste un petit mot pour Patrice, qui à chaque fois fait toujours un travail exceptionnel pour le catering. J'aimerais qu'on l'applaudisse. Merci. Et j'aimerais qu'on remercie encore Cosmogo, notre nouveau sponsor. Stéphane est juste là, il a déjà fait un Keycode et Hexagonal Consulting, qui sont aussi nos long-term relationship sponsors. Tous les speakers de ce soir. Et bien sûr, Ray. Voilà. Merci pour l'accueil.
Thank you.
For being here.
Yeah, pleasure.